To draw electric field pattern, magnetic field pattern, when you have the top view, all right, you are supposed to use the right hand rule, but you know that sometimes it's difficult when you use the right hand rule. So my tip is that use the phrase don't cross. Don't cross. So now when you have a dot like this, then when you have a cross like this, when you focus for the dot, you focus on the N. You draw the N, and then at the end of each N, at the end of the N, you draw arrows. Then the cross at the end, the emphasis is on the S. Then you draw the arrow at the end of the S like this, and this is showing you the direction, right? So here, if I draw the N like this here, so you will have something like this. This is the N. You draw the N like this, as if it is a Z, right? So it means the arrow of magnetic field is going this way. The arrow of magnetic field is going this way, this side. Then you remove the N there, like this. So the electric field lines, with the magnetic field lines will move like this. So you can draw another magnetic field line. Again, you draw another magnetic field line, and then the direction go like this, go like this. Or you can also indicate like this, going like this. They should not touch each other. Going like this, then this is going like that. Right, so it will go like this. Then for a cross, I said if you see the cross, if it's represented by the cross, you are going to draw the S inside here. Draw the S, then at the end of the S is an arrow. It's an arrow. Meaning now, this here is an arrow there. Then this is an arrow. Then you remove the S. Remove the S. We can see that the magnetic field lines are going like that. Moving like this, like that. I can draw another magnetic field line. Alright, should be second. Then still moving like this, moving like this, moving like this, still showing it moving like that. Alright, for this, they shouldn't touch each other. Of course, the art, I'm not good at drawing, so like that. So but in this question here, we are given a cross, and they want us to draw the magnetic field lines. The magnetic field lines around this conductor. So to draw magnetic field lines around this conductor, let me draw my magnetic field. My magnetic field line look like this, and then the direction. Right, first of all, now this is a cross. Because I see the cross, I draw the way the cross has got what? S. So I draw S like this. So it means at the end of S, I draw the arrow. I draw the arrow like that. It means I'm going in this direction, and then at the bottom, I'm going in this direction. Like that. I can draw another. So now I remove the S, remove the S, remove the S. Because the S is assisting me with the direction of the magnetic field. Okay, so yeah, we are using right hand rule. It's just that now it's difficult when you use it. Uh, so I prefer that you use this method because sometimes it's difficult when you use the right hand rule. All right, draw an arrow going like this, going like that. So that is the magnetic field lines. Now let's read the question. A solenoid with a radius of 5 meters. This radius must be converted to meters. Okay. As I'm reading, this is R, the radius, which means that they are talking about something that is circular, right? And then the number of turns, these are the number of turns, is pulled out of the magnetic field with the strength. It's the value 5,20. I said T measures the value of B. So I take it from what? TB. TB, the value of B is measured in T, Teslas, right? That is magnetic field strength, right? Then this is delta X. Sorry, this is delta T time. Right, the solenoid is placed perpendicular to magnetic field. So is this a normal perpendicular or not? Obviously, this is not the normal perpendicular because I don't see the word axis or the word normal. So if it is not the normal perpendicular, then theta is equals to 0 degrees. You're going to use a theta of that is equals to 0 degrees. This perpendicular is informing you about the value of theta. If it was parallel, again it will be informing you about the value of theta that you should use, right? But let's see what they say. State Faraday's law. You should be able to do that. Calculate the magnitude of the magnetic field flask linkage with the solenoid. So here I'm going to say I'm going to use this formula here. Magnetic flux linkage is equals to B A cos theta. Right, already I know this one and I know the theta, right, in the formula. I just have to find the area. And because this is a radius, it means this is the area of a circle, because a circle is the one that has got radius. So the area of a circle is equals to pi r squared. Is pi r squared. Now, now let me do substitution. The value of B is 0, is 5, 20. 5,20. Then A is the area. A is the area. So this is A. And the substitution for A, I will color code it with blue. This is A, and I'm color coding the area. Then, so the area, I'm color coding it with blue. So this is the radius. From 5, what I simply did was to divide the 5 by 100, because from centimeter to meters must divide by 100. So it's 0, it was 0,05. That's why I substituted 0,05 then as a radius. And then the angle is cos 0. So this is 0. This is cos 0. And this is the answer then. this is our answer for magnetic field, the magnetic flux. And then it goes on to say calculate the induced EMF. So for EMF, I'm going to use this formula. Already I have the value of T. It's given to us. We've got the number of turns. We have to get the change in magnetic flux. So here it is just magnetic flux, okay? Initial magnetic flux. But what you see here in this here, it is the change in magnetic. This is magnetic change in magnetic flux. This is just magnetic flux, right? Change in magnetic flux is calculated as follows. Change in magnetic flux is equals to the final flux minus the initial flux. All right. Then, right. So, what we calculated before, it was 0,041 Webers. This one was the initial magnetic flux. Now, when we read the statement, they say this solenoid is being pulled out of magnetic field. When you pull it out, eventually the magnetic flux will become zero because you have pulled it out of the magnetic field. You have pulled it out. So the final magnetic flux will become zero. So here, when I calculate the change in magnetic flux, the final is 0 and the initial is 0,041. And change in magnetic flux will be negative 0,041. 41 Webers. Then I can calculate the EMF by saying EMF is equals to, you have to copy this formula here. You have to copy the formula, negative 350. The change in magnetic force is negative 0,041 over 0,1. And then the EMF is this. So you have to differentiate between magnetic flux and change in magnetic flux. It's not really the same thing. Change in magnetic flux is final minus initial.